This is the lecture for Chapter 2 of your textbook entitled Elements of High-Quality Programs. In this chapter, we're going to learn some things about variables. What are they? How do we declare them? How do we use them? What is a constant? How does a constant vary or different from a variable? We'll talk about arithmetic operations. We'll talk about a concept of modularization of your program. We'll talk about what hierarchy charts are, and we'll talk about features of good program design. So the first thing we're going to talk about is variables and constants. A variable is we'll call it storage place for information you're going to use in your program. Ultimately, that variable has a location in memory where the contents will be stored. Different programming languages have different data types, but we're going to first talk about numeric values. Numeric, as the name implies, is numbers. We may have string values, which would be things like characters or character strings or words or sentences, things that are typically not used in math. As far as numeric values, different languages, like I said, have different variable types. Integer is a whole number, 1, 2, 3, 4, -10, etc. A floating point number, sometimes called a real number, has a decimal value, so 3.14, 10.0, 10.5, etc. What a constant is it's similar to a variable, but basically you set the value once and it can never be changed. A numeric constant, of course, is numeric values. String constants are alphabetic or type strings or words. And then we can actually have unnamed constants. And unnamed constants would be, for example, if you said set x equal to y times 3.14159. The 3.14159 is an unnamed constant. It doesn't have a name, but it is a constant value that you're using in your program. It happens to be the value of pi. As I said previously, variables are ultimately stored in memory, so they can be considered named memory locations. Variables' values can vary over time. They start out undefined. You'll typically assign, for example, x equals 10. That location in memory that's being referred to by x will have the value 10. If you happen to say x equals x times 2, that location would then store the value 20. Most languages require you to declare your variables. Basically, that is saying, hey, this variable exists. Here's its name. And here is its data type. So you might say, for example, I'm going to have an integer whose name is x. The variable's name can also be referred to as the identifier. You've seen code like this before. You've actually written code, but basically you have a variable called myNumber. You're going to read a value from the user. Whatever value they type gets stored into the memory location associated with the variable myNumber. If you then say my answer equals my number times 2, it is going to look up the memory location associated with my number. It's going to retrieve the contents. It's going to multiply that value by 2. Whatever the answer is, it's going to store it back into the memory location associated with the variable myAnswer. A declaration, as we saw on the previous slide, is basically saying the variable exists and this is the data type. An identifier is the actual variable's name. We can declare a starting value. For example, if we have a counter, typically we would say counter equals 0. Counters, we might want to start at 0, then when we get a new value, increment it by 1, etc. Garbage is what they use to refer to a variable's unknown value. Another way to say this, maybe a better way to say it, is when you declare a value in memory, or I'm sorry, when you declare a variable and say, hey, I have a variable x, it is an integer, it gets a location in memory, and really the contents of that location is unknown, or as your textbook refers to it, garbage. You should not assume that it's 0 or any other value. You should assume that it's unknown. If you need to initialize or start that variable at some particular value, then you need to do that in your code. One of the things that we're going to add to our flowcharts is what's called a declarations section. Each program, and soon we'll talk about modules, each module should have a declarations that basically says, here's all the variables I'm going to use, and here's their data type. So in a flowchart, you would use a rectangle like you do for a process step. In pseudocode, you would just put it right after your start statement in the case of the main program. So Figure 2.2 has examples of how to do that, both in a flowchart and in pseudocode. You should pick meaningful names. They call it reasonable and descriptive, but most people are going to say reasonable or meaningful variable names. If you have a counter, for example, you might call it counter. If you're counting the number of lines that you have read from a file, you might call that num lines. So basically, it means give a name that when you go back and look at the program, or when somebody else is looking at the program, they have some idea of what information you're going to be storing in the variable, or what the contents of that variable mean. So you have something called naming conventions, and basically that's when you create identifiers or when you create variables, that is a set of rules, if you will, for naming them. Most programming languages allow identifiers to have letters and digits. Sometimes they won't let you start the name with a digit. They require a letter. Some programming languages allow you to have things like underscores or dashes in identifier names, but again, that's very specific to each of the languages. The language also has something called reserved keywords that you cannot use. So, for example, most programming languages have an if statement. It may be a rule for creating identifier in that language that you cannot use any keywords that are already used in the language. So some languages would not allow you to have a variable called if, because it's already part of an if-then-else statement, for example. Most languages, variable names are case sensitive. That means if you declare the variable as lowercase abc, you assign a value to lowercase abc, then you cannot, or if you then try to output the value of ABC, that is not, or I'm sorry, capital ABC, that is not the same variable, so you will not get the results most likely that you would expect. There's different styles of naming variables. Camel casing is basically using words to describe the contents of your variable. Here we have somebody's hourly wage, it would appear. The first word is all lowercase. Any words that appear after that first word would have their first letter capitalized. So there's an example there on the slide. Be descriptive. It must be at least one word. It must start with a letter. And again, it should have some meaning that is appropriate or related to the contents it is going to store. So they have a whole bunch of things called, we saw camel casing. They have something called Pascal casing. Several decades ago, a lot of times the first language you learned in computer science was a language called Pascal. In it, you used words crammed together, and the first letter of every word was capitalized. They have something called Hungarian notation, which is basically camel casing, but you put the data type in front of it. A lot of languages would accept that. I don't know that that's used very often. Snake casing is basically where you take words and you can't have a space usually in identifiers. So instead of putting a space between words, you put an underscore. I kind of like to do that. I use snake casing or camel casing mainly. You can have mixed cased with underscores, and then you can have kebab. I guess it's supposed to look like a kebab where you've run a metal or wooden skewer through the variable names. But basically all it's saying is that you're putting a dash or a minus sign between the different words in the variable names. In assignment statement, you have been using these. You may not have known that it was called an assignment statement. Basically, an assignment statement is a statement that sets the value of a variable. So in this case, we're saying set my answer to my number times 2. And what that's doing is looking up the values currently stored in my number, multiplying it by 2, and then the equal means assigned to. So you would assign to my answer the value my number times 2. Several things. The equal sign. In programming, you really should get used to reading the equal sign as not equal, but get set to, because equal is kind of vague. It could refer to a quality, which we'll talk about later. Multiplication is a binary operator. A lot of times people hear that and think it means it works on binary numbers because they know computers work in binary. But really what it means is it requires 2 operands. So we have an asterisk, which means multiplication. It's going to operate on 2 numbers. In this case, the value that is before the star and the value that's after. So it'll take my number and multiply it by 2. One thing that we have to worry about in expressions that have multiple operators is something called associativity. That basically means if we have operators of the same order of precedence, which we haven't talked about yet, but that should happen at the same time. Like if we have a whole bunch of multiplications, is the multiplication going to start with the leftmost multiplication and work to the right, or is it going to start at the rightmost and go to the left? Now, you may recall from elementary school or middle school them saying, for example, that addition is associative. That basically means if you have a whole bunch of additions, it doesn't matter what order you do the additions in, you're going to get the same answer. Multiplication is associative. But the problem comes in if you have addition, subtraction, multiplication, division all in one big statement, then things need to be done left to right or right to left, whatever the correct associativity is. Because if you do it left to right and then you do it right to left, and possibly in some other order, you're going to get 3 different answers. The value on the left-hand side of an equal sign is referred to as an L value. An L value is a left operand. That means it is anything that would be appropriate to appear on the left hand of an assignment statement. An example of something that's an invalid L value is if you said 3 equals 4 times 5. 3 is not a memory location. It is not a variable, so it doesn't make sense to be trying to store something into a constant value 3. So 3 is not a valid L value, but variable names are, and that's typically what we will use. Numeric values, going back and looking at data types, they hold numbers, which are digits. If it's something other than an integer number, it may have a decimal point, it may have a sign like positive or negative, and we perform mathematical operations on numeric values. String variables can hold text. These are letters of the alphabet, along with some special characters like space, underscore, question mark, exclamation mark, anything that we might appear in a sentence. Type safety prevents assigning values of an incorrect data type. So if we said something like numeric value x equals double quote TWO, double quote. So it looks like we're trying to assign a numeric value to. Well, the reality is TWO is a string. We cannot stick a string into a numeric value. Languages that enforce that are called strongly typed languages. There are other languages that would do things to try to perform some type of calculation, but in the beginning you usually deal with strongly typed languages where you have to do mathematical operations on numbers, store the result in a numeric variable, or do some kind of string operation on strings and then store the result in a string variable. You can't mismatch those. A named constant is similar to a variable. Like I said previously, it can only be assigned a value once, and it can never change during the program's execution. So a lot of times we might do something like create a variable called sales tax and set it to 0.06 if the sales tax rate was 6% in our area. And then instead of saying price times 0.6, we could say price times sales tax, which may make more sense to somebody looking at the code of our program, which is not exactly familiar with what we're doing. There are lots of arithmetic operations that you can perform. Usually the first ones you deal with are ones that we use on a regular basis: addition, subtraction, multiplication, and division. We're used to using a plus sign for addition and a minus sign for subtraction. From assignments you've done and reading in the book, you're probably used to using an asterisk or a star as multiplication. And I don't know if we've seen it yet, but if you want to do division, that is a forward slash. That's the character that we use to represent division in most programming languages. So I mentioned rules of precedence earlier. Basically, it is the order that operators are evaluated in. So making it easy, if we have the four we talked about before, multiplication and division, addition and subtraction, we're going to do all multiplication and division first. Once we've done all the multiplication and division that appears in an arithmetic expression, then we're going to go back and do all the additions and subtractions. On top of that, if we have multiple multiplication and divisions within the statement, we're going to evaluate them left to right. When we go back and do the addition and subtraction, again, the associativity of addition and subtraction is left to right. So the precedence refers to what do we do first, and you'll see up at the top that sometimes it's called order of operations. And then once we have multiple operators of the same level of precedence, the associativity says, do we evaluate them left to right or right to left? So here's a precedence chart that has some of the more common ones. The set to, or the assignment, is the last. You'll notice that its associativity is right to left, which may seem a little strange, but in a lot of programming languages you can say A equals B equals C equals 2, and that will actually have the end result of setting A, B, and C to the value 2. This associativity and precedence chart is very small. I often teach the Perl programming language. The precedence and associativity chart for the Perl programming language, and really any language if they show it in full, takes up at least a whole page, if not flows a little bit onto a second page in the textbook. So there are lots of operators that you can have, but these are the more basic ones that are easy to understand, easy to start with, and all languages have them. So they're talking about the integer data type. Again, integer is the same as whole numbers. A lot of languages have what's called integer arithmetic. Basically, if you divide one integer by another integer, any fractional part would be thrown away. So if you were doing integer arithmetic and saying 5 divided by 2, then the answer would be 2. If you were doing it with whole numbers, obviously 5 divided by 2 is 2.5 or 2.5. There is something called the remainder operator or the modulus operator. I prefer to call it the modulus or mod operator. Basically, that is the way to get the remainder of a division operation. And this is very, very handy in a lot of things, but encryption is one example. So 24 mod 10, the way you would think about that is you would do kind of third grade math where you didn't know about fractions, you didn't know about decimal values. So, your teacher would say, you have 24 items, how many times can you take 10 items from that? And your answer would be 2. How many of those items do you have left over, which would be the remainder, is 4. So if we're doing integer math, 24 divided by 10 is 2. 24 mod 10 is 4 because it is the remainder of 20 divided by 10 if you're using integer arithmetic. Another programming feature that is considered good design is called modularization. Basically, they call it a subunit of a programming problem. The way I like to think about it is you have a big problem, there's lots of pieces, and a lot of times you can solve these pieces individually and put the code associated with solving a portion of the problem into something called a module. Other programming languages will call it subroutines, procedures, functions, methods. These are all words for module, and which one your programming language uses will vary, but those 4 are very common. The way you invoke or call a module is by using its name, causing it to execute. A lot of times you will pass something called arguments, which we'll talk about in a bit, to the module. It'll need those values to execute. Modularization allows you to break your program down into smaller parts. Usually if you do that, it's a lot easier to think about the parts that you're solving one at a time. And typically if you do that, instead of thinking about the entire program as one big problem, you're going to be less frustrated. You're probably going to write the program quicker. And on top of that, your program is probably going to be more likely to function correctly the first time or with minimal debugging. Modularization, there's several advantages to that. One is it provides something called abstraction. Basically, you can come up with a word or a module name for what you're doing, like get input values. I'm going to get input values from the user. Then I'm going to solve a problem. Well, get input values may go off and get X, Y, and Z. Return those back to your main program, and then solve problem, you might pass it X, Y, and Z, and then it performs some calculation on X, Y, and Z and gives you the answer back. So it can kind of let you think about your program at a very high level without getting down and having to go statement by statement by statement. One call or one statement may refer to lots of different program code, which on top of that may correspond to many, many, possibly dozens of machine instructions. So we talked about assembler language or machine code in Chapter 1. Modules are one way to achieve this type of extraction. Another advantage of modularization is it allows multiple programmers to work on the same problem. So if you have Module 1, Module 2, and Module 3, granted those are not very well named identifiers, and you have three people working on this, you can say, okay, person 1, you go write Module 1, person 2, you go write Module 2, person 3, you go write Module 3. We have some specifications, And then what will happen is we'll pull those all together. And if person 1, 2, and 3 wrote to their specifications, you should be able to put those 3 modules together in a program and have it work correctly. They have a statement here: rarely does a single programmer write a commercial program. If you've ever looked at the credits for a software program like Photoshop, it may list 20 or 30 names. So big programs, big applications typically have groups of people that work together on them. And by using modularization, that allows them to kind of work independently of the other programmers and put everything together and then test it. Another advantage of modularization is it allows you to reuse your work. If you have something that calculates sales tax and then you're writing another program that needs to calculate sales tax, then you can just pull your sales tax module from your first program, plug it into your second program, and hopefully it already works correctly. It does exactly what you want, and you don't have to reinvent the wheel or rewrite the code. Another one is it allows you to divide your testing down, and you have reliability. It's easier to test modules, and as I said before, once you've already tested it and know it works correctly, you should just be able to reuse it and have it work reliably. When you modularize your program, you have a main program, which is the very top level of your program. If your main program calls modules, or you have modules that call other modules, you're going to have a header that talks about the module, declares any variables the module is going to use. You have a module body, which is your code for the module that helps it perform whatever calculation or task it's supposed to be doing. And then at the very end, you have a return statement. The return statement typically has 2 functions. One is it returns the flow of control of your program from the module back to the location in the main program that called it. It may also allow you to return values. So if you passed a value in, it was supposed to perform some mathematical calculation. The return statement will tell you what the answer of that mathematical calculation was. Modules have names, or at least in most programming languages. In Perl, you can have anonymous functions. But right now, we'll assume that all modules have names. The naming convention for modules are very similar, if not identical, to the naming convention for variables in your programs. And if you need to, sometimes the parentheses are required. If you don't need to pass any information into the module for it to perform its task, you will just have an empty set of parentheses. If you have values that you need to pass into the module, those are referred to as arguments. They would be a comma-separated list of arguments within a set of parentheses. When a portion of your program, they say the main program, but really any portion of your program, wants to use a module, it does what's called calling the module or invoking the module, and it does that by using the module's names. In flowcharts, there's a couple of ways to represent modules. If it's a module that is within the same program that you are flowcharting, then you have a rectangle with a bar across the top. You have the name of the module inside the rectangle, and then separately the module has its own flowchart symbols and its own sentinel values and its own terminators, like the return statement to get back to the main program. If you're calling a module that exists somewhere outside the program, it will be in a rectangle with bars on the left and right side. I'm not sure when they introduce you to that in the textbook, if at all, but that's an external module. So here you see that we start our program. We have our declarations, which we are now going to use in all of our flowcharts. We input some information. We output 3 sets of information, actually 4 or 5, and then we stop. So basically, we have code that only uses a main program. Now the problem is we probably want to generate a bill for multiple people. So what we're going to do is take the statements out of the main program that relate to generating one bill and encapsulate those into a module. So basically what happens is it looks like this. We have declarations, we input a person's name and their balance, and then we generate display address information, and then we output their balance. So over on the right, with its own terminal symbol, that is the kind of rectangle with rounded ends, we have display address information. We have declarations for that routine, and then it outputs line 1, 2, and 3. In real life, we would be reusing line 1, line 2, line 3 each time we called this for different customers. But for the time being, to make the example easy, the top half of this diagram shows how to do it in a flowchart. The bottom half of the diagram shows what this would look like in pseudocode. Again, it is important to note that the main program declares some variables that it uses, and the module declares some variables that it's going to use. So we have declarations in both locations. Any statements that we can have in our main program can be placed in modules. We can have variables, we can have constant values, we can input information, we can output information, and we can process or calculate information. Now, one thing that sometimes people have trouble with is the concept of variable scope. Basically, what scope means is where can a variable be seen. And most programming languages have two types of scope. They have global and they have local. So what they're talking about here is locally scoped variables. A locally scoped variable is declared in a module. It can only be seen, which means you can read its value, you can change the value, you can manipulate the value. That can only be done within the module if the variable is local. If it is global, the whole program can see it. So if we have a global variable A, we can manipulate A, use A in the main program, or any modules that appear within our program, which is what this is talking about. It's declared at the program level. So any of those variables you declare right after the start symbol or right after the start of your pseudocode is referred to as a global variable, globally scoped. They can be seen anywhere. You can have problems using global variables. You know, before the example where we had 3 people coding, if they all used a variable x and declared it global, then we might have an x in our code. We call persons2 module. Their value of x would destroy our value of x, which would then make it look like our module, our code was not working correctly. So typically you try to avoid global variables. There's a few reasons to use global variables, but you know, for things you're doing in a module, you definitely want to declare local variables. They like to divide the programming task into several parts. They like to say, okay, we have declarations at the top. We have housekeeping tasks, which are things that we need to do to set up for the program. This would be like initializing values. So if we had a variable pi, we might say pi equals 3.14159. Okay, so now we can use pi and it has the correct value in it. Then we have a detailed loop, which is the core work of the program. And then we have end of job tasks, things you need to do at the end of the program, writing information out to a file. If you opened a file, close a file, that type of thing. So they seem to really like this flowchart, and I think it's fine for a example of modularization and also kind of those 4 features that we just talked about. But you shouldn't write programs that say housekeeping, detailed loop, end of job, and just use this over and over again as is. You need to have meaningful variable names, initialize and input values, perform iterative loop, and then clean up, close files, that type of thing. You should have more meaningful names that relate to whatever task you're trying to perform. Again, notice in the flowchart that housekeeping, detail loop, and end of job have the internal module symbol, which we've just learned about. A hierarchy chart is basically a picture. It's not a flowchart. It's a picture of how modules are related to one another. So it's basically what modules do other modules call, and or what modules does your main program call. This can be a planning tool to plan out modules and how well you thought them out. And it can also be used as a documentation tool, either for yourself when you come back and look at the program, or if you're on a team of programmers, the team can look at the documentation. Another example would be you write this program, you leave the company, somebody else now has to look at your program, so it can be documentation for them to come back and figure out what you were thinking in your program or how the program works. So here we have a figure that basically says the first one is a payroll report. So we have a main program, we have housekeeping, we have a detailed loop, and we have end of job. Those are all called by the main program. Now then, in a more complicated example, housekeeping calls get order, detailed loop also calls get order, but it calls process order. Process order calls 3 modules, and out of those 3 modules, compute bill calls compute tax. So basically it's showing what modules call what other modules. So you have some idea how your program is functioning. Another thing that's very important to use is comments. Comments are sentences that you put in that explain something about your program, but they are not compiled or looked at all by the program. So if you have some big long numeric computation that it's not obvious what it is right offhand, you might put a comment before it and say, hey, I need to calculate this value, and that's what this formula does. Your identifiers, which would be variables or module names, need to be very carefully chosen. You need to make your statements that you're executing easy to read. If you prompt a person for a value, basically what prompt means is to tell them what you're looking for. Hey, you need to enter a value of X, or you need to enter your pay rate, or you need to enter your name. That's prompting the user, explaining to them that you want information, and on top of that, more importantly, what information do you want, and then they'll type in a value. They say you should echo the input, but we're not going to have programs that say, give me your name, and I type Wayne Beach, and it says, hey, you just typed Wayne Beach. That's, in my opinion, a tad redundant. There might be some cases where later you will echo that with maybe, the person's name and how much money you owe them for the month's work or something like that. But here it implies you should echo it right after you input it, which is not really the case. Learning good programming habits takes time. You just need to practice those. As I grade assignments, if you do things that are not good programming habits, for example, you name your variables A, B, and C, I will, in the beginning, write comments and say, hey, those are not meaningful variable names. And if you persist in doing that throughout the semester, then probably at some points points will start to get deducted for having poor programming habits. We talked about comments already. I said they were written explanations of what you're doing. They are not part of the program logic. That's where I said they are ignored. And they serve as documentation either for you coming back and reading the program later or somebody else reading your program. Now, you can go overboard on modularization and ultimately make things more complicated than they should be. And you can also go overboard on program comments. And the way you go overboard on program comments is by saying, hey, this next line multiplies by x by 2 and stores it in A. And the line of code is A equals x times 2. That's pretty obvious what's happening. Typically, you'll take a chunk of code and say, hey, I'm performing the calculations needed to solve the quadratic equation. And then you have 4 or 5 statements that do that. Syntax, we talked about this in Chapter 1, is basically the grammar for a programming language. Syntax differs between programming languages. So when we get down to doing something, we'll probably start with BASIC. We'll need to know what the syntax for BASIC is. At some point, I might have you play around with another language. One of my favorites is Perl, maybe Python. We'll see that the syntax and the syntax rules will be slightly different. You've been using a flowchart. Basically, flowcharting helps you solve the problem and allow somebody else to read it by using correct, well-known things like a diamond as a decision point, that type of thing. Here's an example of comments within the declarations. SQ feet is an estimate provided by the seller of a property. So it looks like somebody's going to say, hey, my house is 2,300 square feet. The price per foot, whatever market you're in, a lot of times houses, they'll say average price in this neighborhood is $70 a square foot. And then lot premium would be an amount that would be added, it appears, if there's certain amenities like waterfront, or maybe it has a pool or something like that. So they've tried to use meaningful variable names. But, if I just said, hey, I'm writing a program and I have a variable lot premium, it might not be obvious right offhand to you what lot premium is. So by using comments, in this case 2 slash signs, 2 forward slashes next to each other, we can put comments that explain what the different variables mean. Now, they put the comments after the variable. If the language allowed it, I personally would put it on the same line as the variable. And if the language did not allow that, I would actually put it before the declaration. But any of those are good programming style. The main thing is you need to include meaningful, useful comments in your program. Here's a flowchart that has something called annotated symbols. Basically, annotated symbols are your way to put comments in a flowchart. So you have a dashed line over to a box that says, has things. Like the first one, we have a pay rate, it looks like, of $13. Hey, we expect that to be increased on January 1st. Down here where they're calculating pay, they're saying this program assumes that everybody makes the same pay rate. Maybe that's a reasonable assumption for your company. Maybe it's not. But anyway, it is commented to point out that fact. So if you need to explain something or make notes, you would do that with what's called an annotation symbol. And notice that the annotation symbol, I said it was a rectangle. It's a rectangle that does not have a right side. It's kind of a sideways U shape. As far as choosing identifiers, usually variable names would be something that in English we would refer to as a noun because they represent something. Modules perform actions on variables usually, so we would name them as a verb. If you use meaningful enough, good enough names, you can refer to your program as being self-documenting. That is, somebody can look, and because you've used really good names, they can kind of figure out what the program does without any additional documentation. You should use pronounceable names so that if you're talking about your program or your variables, you can actually pronounce them and it's much easier to talk about. You should minimize your use of abbreviations, and you should avoid digits unless there's a really good reason to put digits in your variable names. Multi-word variable names are good. Use underscores, use dashes, whatever your programming language allows. A lot of times we have something called external documentation. That's documentation that goes along with our program that's not part of the program. Or we may have self-contained documentation, which is documentation you put in the same file as the program. In either of those cases, a lot of times you have something called a data dictionary. And basically, a data dictionary is a list of here's all the variables I'm using in my entire program and all my modules, and here's what they mean. So somebody can look at that and see what type of information they need. Most languages, if you have a long statement, will allow you to break it across multiple lines. Try to avoid breaking in awkward or confusing locations, so if somebody looks at the code, they can't figure it out. One way to avoid line breaks at all is to do a calculation, let's say a complex calculation in 5 steps, using temporary variables, making our statements longer, and then at the very end using the temporary variables to perform the final calculation. Most modern programming languages are free-form. That means white space doesn't matter. You can put blank lines in. You can space over a little. You can put line breaks wherever you want, but you need to make sure you do it in such a way that your program is readable. That means it makes sense to somebody else. Typically, it is bad programming style to combine multiple statements on one line. Usually you try to do one statement per one line of code. Temporary variable that I mentioned before is referred to as a work variable. It's just a work location or a temporary value to store information that you're working on. So here's an example. We have a big long calculation at the top that almost takes up the whole line. In worst case, it might flow over 2 or 3 lines. So what we can do is we can say the base property price is the square foot plus the price per foot. The total sale price is that value in a temporary variable, base property price plus lot premium. And then we have a salesperson commission, which is going to be the total sales price times the commission price. So we use 3 statements and temporary values to calculate the salesperson commission instead of putting that in one great big statement like we have at the top. We've already talked about this. A prompt is a message telling the user what they're supposed to do. It lets them know they're supposed to input values. Hopefully it tells them what type of value they're inputting. And echoing the input back, like I said, maybe we do that, maybe we don't. It really depends upon the situation. So here's a start of a program. We have declarations. We ask for a person's name and their balance, both in flowchart and pseudocode format. Here we would actually prompt and say, please enter a customer's name. Somebody types the name, they input it. Please enter the balance due. Then they read that. So breaking it down, prompting them individually for pieces of information that the program needs. Good programming habits. Here's a list. If you plan before you code, the worst thing to do is to say, okay, I read the problem, I'm going to sit down, I'm going to start typing code. Really what you need to do is think about the program, how you're going to solve it, draw a flow chart or write pseudocode, whichever you're asked for or whichever you prefer. Then desk check your logic on paper. So kind of go through and run through what you're going to do. I'm going to ask the person for a user. Okay, they put 3 in. I would perform this calculation. So basically pretend you're the computer. I might do a separate video on something called program tracing, which would fall under the category of desk checking, or it would also fall under the category of debugging your program if it's not working correctly. Think about how you're going to name variables and modules, and then write program code that is easy to read. So, not going to read over these, but this is the summary of things that we talked about and that you should have gotten out of Chapter 2. So that concludes the Chapter 2 lecture.